Hello, my dear grade 10 learners. Welcome to my class. I am Teacher Lourdes, your science teacher for today's session. These are the learning goals for this session. Number 1. Differentiate between concave and convex lenses. Number 2. Locate and describe the images formed by concave and convex lenses. And number 3. Cite some uses of concave and convex lenses. But before we proceed to our lesson, let us recall the different types of images formed by spherical mirrors. In this diagram, an object is placed beyond the center of curvature of a concave mirror. Can you guess what type of image will be formed? Yes, the image formed is reduced, inverted, and real. If the object is placed at the center of curvature, what will be the characteristics of the image? Very good. The image is of the same size as the object and it is still inverted and real. In the next figure, the location of the object is between C and F. Who can describe the image that will be formed? Your answer is correct. The mirror will form an enlarged, inverted, and real image. How about if the object is located between the focus and the mirror? How will you describe the image that will be formed? Yes, the image is enlarged, and it is already upright and virtual. So, the concave mirror forms the following types of images. 1. Reduced, inverted, and real. 2. Same size as the object, inverted, real. Number 3. Enlarged, inverted, and real. And the last one is enlarged, upright, and virtual. Unlike concave mirrors, the convex mirrors always produce images that are reduced, upright, and virtual. Now, can you give other examples of materials or devices that can produce an image of an object? Examples of these materials are those found in optical devices. Optical instruments like cameras, projectors, microscopes, binoculars, and telescopes have drastically widened our view of the world. Eyeglasses allow millions of people to read and see in comfort. Have you ever wondered which optical component makes all this possible? It is simply a lens. Lens is a material that bends or refracts light rays. There are two main types of lenses, the concave lens and the convex lens. How does a concave lens differ from a convex lens? A concave lens is a kind of lens that is thicker at the edges and thinner in the center. It is also called a diverging lens because parallel light rays spread out after passing through the lens. While a convex lens is a lens that is thicker in the center than the edges. This lens is a converging lens because when parallel light rays pass through it, the refracted rays meet at a single point called the principal focus. What do you think are the types of images formed by these lenses? Are they similar to the images produced in spherical mirrors? To find the answer to these questions, you must perform activity number 1. You will need the following materials: double convex lens, lens holder, or you can also use modeling clay, white screen, meter stick, and lighted candle. You have to do the following. Number 1. Place a ruler or meter stick on a table. Number 2. Place a convex lens on a stand or holder vertically along the meter stick. Then, you're going to use the white screen to locate the image of the window or the distant object. Move it backward or forward until a sharp, inverted, and smaller image is formed on it. The distance between the screen and the lens, or between the image and the lens, equals the focal length. Number 4. Mount the convex lens on a clay or lens holder. Place the lens at the 0 mark of the meter stick and place the candle in front of the lens at the 70 centimeter mark. On the other side of the lens, place the white screen in an upright position. Then move the screen backward or forward until a clear image of the candle is formed. Number 6. Describe the characteristics of the image formed. Then write your answer in the last 3 columns of Table 1 in your activity sheet. And number 7. Repeat steps 4 to 6 for the following object distances. DO equals 2F. Between F and 2F. And between the lens and the focus. You must also take note of the location of the image formed at different object distances. Okay, class, you may now perform this simple activity. The procedure can also be found in your activity sheet number 1. Are you done with the activity?
Yes.
Good job! Now, let us discuss the answers in Table 1. At DO equals 70 centimeters, or when the candle is located beyond 2F, the image is real, inverted, and reduced. When the object is located at 2F, the image is real, inverted, and of the same size as the object. Next is between F and 2F. At this location, the image is real, inverted, and enlarged. And when the object is located between F and the lens, the image is virtual, upright, and it is enlarged. Were you able to get all the right answers?
Yes.
Good! So, these are the images formed by the convex lens. Now, based from your observation, how is the size of the image related to the object distance? Very good answer. As the object distance decreases, the size of the image increases. Or, as you move the candle towards the lens, its image becomes bigger. And how is the object distance related to the image distance? Yes, as the object distance decreases, the image distance increases. But in the last procedure, when the object was placed between F and the lens, no image was seen on the screen. It's because the image was formed on the same side of the lens as the object. This image is called virtual image. Did you get all the right answers in the activity? Very good! And for doing such a great job, you will receive this one. Now, I want you to look through this concave lens. Observe the size of the image of the candle and its orientation at different object distances or location. What conclusion can you draw from this activity? That's a good answer. A concave lens always produces virtual, upright, and smaller image of an object. Okay, the following diagrams show the images formed by the concave lens at different object locations. Again, how will you describe the characteristics of the image? Very good. The only type of image produced by the concave lens has the following characteristics: virtual, upright, reduced. Now, consider these diagrams. Then try to explain how the image distance is related to the object distance. So, what happened to the image distance as the object distance decreases? That's correct. As the object distance decreases, the image distance also decreases. And what can you say about the location of the image? Yes, the image is always located between the focus and the lens. Another way to determine the characteristics of the image and its location is by applying the lens equation. It is expressed as 1 over f equals 1 over do plus 1 over di, where f represents the focal length, do means object distance, and di is the symbol for image distance. Then, to solve for the magnification, we have the formula m equals negative di over do. We can also use the formula m equals hi over ho. M represents the magnification, hi means height of the image, and ho is the symbol for the height of the object. The magnification of a lens means how large or how small an object can be reproduced on the film or image sensor. Now, let's try to solve this problem. A 30 centimeter tall robot is placed 20 centimeters away from a convex lens of focal length 15 centimeters. Find the following. Letter A, image distance. B, magnification. And C, height of the image. Describe also the characteristics of the image formed. Now, who can identify the given data? Very good. So, the following are the given data. HO equals 30 centimeters, DO equals 20 centimeters, and F equals 15 centimeters. To solve for the image distance, we will use the formula 1 over F equals 1 over DO plus 1 over DI. Then, substitute the values for F and DO. So we have 1 over 15 centimeters equals 1 over 20 centimeters plus 1 over DI. After substituting the values, we have to transpose 1 over 20 centimeters to the left side of the equation. We must also change its sign from positive to negative. So, our new equation will be 1 over 15 centimeters minus 1 over 20 centimeters equals 1 over di. In your lesson in mathematics, you have learned that in order to subtract fractions with different denominators, you have to find the LCD or the least common denominator. So, in this example, what do you think is the least common denominator? Very good. The LCD that we can use in this equation is 60. Then, divide 60 by the first denominator and multiply the result by the numerator, or 60 centimeters divided by 15 centimeters equals 4 times 1, which is the numerator. This will be equal to 4 over 60 centimeters. Repeat the process for the second fraction. So, 60 centimeters divided by 20 centimeters equals 3, multiplied by 1. This gives us an equivalent fraction of 3 over 60 centimeters. In the next step, we will simply subtract the numerators that we have in our new equation. The result will be 1 over 60 centimeters equals 1 over di. To find the image distance, we will get the reciprocal of both sides of the equation. The reciprocal of 1 over 60 centimeters is 60 centimeters over 1. And the reciprocal of 1 over di is di over 1. So, our new equation will be 60 centimeters over 1 equals di over 1. Then, 60 centimeters divided by 1 is equal to 60 centimeters, and di over 1 is equal to di. So, the image distance di is equal to positive 60 centimeters. A positive image distance corresponds to a real image. On the other hand, a negative image distance indicates that the image is virtual. Okay, class, let us now calculate the magnification using the formula m equals negative di over do. Our image distance is 60 centimeters and the object distance is 20 centimeters. By substituting these values, we have m equals negative 60 centimeters over 20 centimeters. Then, we will simply divide 60 by 20 and cancel the unit centimeters. So, our final answer for magnification is negative 3. Now, to solve for the height of the image, we will use the formula m is equal to hi over ho, or magnification is equal to the height of the image divided by the height of the object. The magnification is equal to negative 3 and the height of the object is 30 centimeters. Our equation becomes negative 3 equals hi over 30 centimeters. This equation can also be expressed as negative 3 over 1 is equal to hi over 30 centimeters. Now, what will be the next step in order to solve for the height of the image? Yes, we will apply the cross multiplication method. Negative 3 times 30 centimeters equals 1 times hi. Therefore, the height of the image is equal to negative 90 centimeters. To describe the orientation and the size of the image, always remember the following. If the absolute value of the magnification is greater than 1, the image is enlarged. If it is equal to 1, the image is of the same size as the object. And an absolute value of the magnification that is less than 1 corresponds to an image that is reduced or diminished. Now, our final answer for the magnification is negative 3. And its absolute value is 3, which is greater than 1. So, how will you now describe the size of the image? Your answer is correct. Since the value is greater than 1, therefore, it is an enlarged image. The sign of the magnification tells us the orientation of the image. A positive magnification implies that the image is upright, while a negative magnification signifies that the image is inverted. By applying the sign conventions, we can say that the image is inverted because the magnification is negative. Did you understand, class? Okay, who can describe again the characteristics of the image? Very good. The image is real, inverted, and enlarged. Lenses are essential to our lives. We're able to see because each of our eyes has a lens that produces an image of the world around us. In fact, all the optical devices that are part of our everyday life make use of lenses. What are the uses of convex lens? Convex lenses are used in spectacles for the correction of a special type of eye defect called hypermetropia or farsightedness. It is an eye condition that makes it difficult to focus on near objects. How can this type of eye defect be corrected using a convex lens? Normal vision occurs when light is focused directly on the retina. But in a farsighted eye, the image is formed behind the retina rather than directly on it. It may be caused by the eyeball being too small or the focusing power being too weak. To correct this type of eye defect, convex lens is used. It bends or converges the light rays and causes the image to form on the retina. Another example of optical device that uses convex lenses is the microscope. It is an instrument that is used to magnify very small objects. In a compound microscope, two sets of lenses are used: the objective lenses and the eyepiece lens. The objective lens forms the first real and enlarged image of the object, and the eyepiece lens forms the final image, which is virtual and enlarged. A camera is an optical instrument that forms and records an image of an object. Most cameras use combination of concave and convex lenses. They form real and reduced images, which may be recorded on film or may be detected by an electronic sensor that stores the image digitally. Next is the magnifying glass. It is a convex lens that is used to produce a virtual, upright, and magnified or enlarged image of an object. A telescope is an optical device used to form images of distant objects. Most simple refracting telescopes have two sets of convex lenses, the objective lens and the eyepiece lens. The objective lens forms the first real, inverted, and reduced image of a distant object. And the eyepiece lens forms the final image, which is virtual, upright, and enlarged. Who can give an example of an application of concave lens? Yes, concave lenses are used in eyeglasses for the correction of a special type of eye defect called myopia or nearsightedness. Myopia is the inability of the eye to focus on distant objects clearly. This eye defect occurs when the cornea is too stiff or the eyeball is too long. In a nearsighted or myopic eye, light from distant objects come to a focus in front of the retina. As a result, objects at a distance are blurred while nearby objects are clear. Concave lens is used to correct nearsightedness. It diverges the light rays before entering the eye and causes the image to form on the retina. This type of lens is also used in telescopes. Some telescopes use a combination of concave and convex lenses. The convex lens is used for magnification and the concave lens as the eyepiece. Another example of device that uses concave lens is the peephole. It is a small security device that provides a panoramic view of objects and environment outside the door. These are just some of the uses of concave and convex lenses. For more applications of these lenses, kindly click the following links. That's all for today. Thank you for watching. Bye-bye.